Hello everybody, welcome back to Networks class. So last time in class we did the following. We discussed how to solve shortest path as a linear program. And then we saw some definitions on graph structure, so you should know about what a tree is, for example, now. And at the end of class we just started the problem of graph search. And we just talked about this algorithm breadth first search. We wrote down the pseudocode for it, but we haven't done an example with it yet. And so that's where we ended class. And the plan for today is to just go over some of the answers to homework 0 and some of the important lessons to be learned from those homework problems. So let's just get started into that material. So I'm not going to go over the problem statements here, so I'm assuming that all of you have read them and have thought about them for quite a while. So the answers to number 1, I'm going to read very carefully. I'm very interested in the kinds of things that you guys have done before coming to class here. And you can read my answer a little bit over there. For number 2, the question asks, what's the difference between a graph and multigraph? You should all know this. A multigraph allows us to repeat edges, and a graph does not. The second part of the question is, in an undirected graph with self-loops, are the edges described using a tuple set or a multiset? Well, it's undirected, so direction doesn't matter, which means it's got to be a set or multiset. And it has self-loops, which means we need repetition, so it's a multiset. Number 3, you can just read the answer to that one. It's pretty straightforward. Number 4, okay, so here I asked you to write down the adjacency matrix of a graph and then transpose the matrix and draw the graph that corresponds to the transpose matrix. So if I have a graph whose adjacency matrix is A, and I have a graph whose adjacency matrix is A transpose, then this graph is basically the reverse graph of the original one. And you should have seen that from your answer. And just kind of one side comment to make about this, which is that for an undirected graph, what do you suppose the relationship is between its adjacency matrix and the adjacency matrix transpose? Well, since the graph is undirected, when we reverse the edges, we should be getting the same graph. And that's indeed what happens here, is that A is actually equal to A transpose. So for an undirected graph, the adjacency matrix is symmetric. Okay, so that's the big punchline from number 4, is that when we take transposes, we reverse things. So number 5 just gave you a little bit of practice on putting a matrix in the various sparse matrix formats. Number 6 is just doing the reverse. If somebody gives you a sparse matrix format, to be able to read things back and reconstruct the graph. So number 7 is probably the first question that I got a lot of questions on while you were working on your homework assignment. So let's write down what the question is. So for this question, we're given a matrix A in compressed sparse row format. And for part A, we want to return A transpose in compressed sparse column. And so if you read the hint for number 7a, you should have found that A in compressed sparse row is actually the exact same thing as A transpose in compressed sparse column. So no work needs to be done here. So in just O of one time, you can return the right answer. So for part B, that's a little bit more complicated. So for part B, we wanted to return A in compressed sparse column. So now we actually have to do some translation, starting from A in compressed sparse row and ending in A in compressed sparse column. So let's see how much work that takes and how to reason about doing that. So to do this, let's just use the example from number 5. So the example from 5 was the following matrix. So 1, 2, 3, 4 zeros here. 11, 0, 0, 12, 0, 13, 0, 0, and 14, 0, 15, 0. So that was the matrix A. And here's the matrix in compressed sparse row format. So we have an index pointer. We have a columns array and a data array. And index pointer looks something like this. 0, 0, 2, 3, 5. And the columns array looked like 0, 3, 1, 0, 2. And the data array was just 11, 12, 13, 14, 15. Okay, so we want to start with compressed sparse row. So imagine that we don't know the matrix, we just know this compressed sparse row format. And we want to end in compressed sparse column. So here's our plan. We're going to start with compressed sparse row, and we're going to take that first to column-based linked list. So let's see how much work that takes. So here's a column-based linked list that we're going to construct. So here we need a column number, rows list, and a data list. So this matrix has 4 columns, so here they are, 0, 1, 2, 3. And I have to have some kind of row list for each one of them. So here I started everything. And so my first question is, how much work did I just do in constructing what I've constructed so far? Well, right now I've done O of n work because I had to construct just empty lists right here, these n empty lists, one for each column. And so in a program, this would be some kind of for loop that just creates these n data structures. So we've already done some work. That's the O of n work. So now let's go about trying to populate these lists and actually put down the numbers. So to do that, I have to go look at this CSR and figure out where each row starts and stops. So this was row 0 here. It starts at 0 and stops at 0. Row 1 starts at 0 and consumes 2. Row 2 starts at 2 and consumes 1. And row 3 starts at 3 and consumes 2. So just to do those calculations, how much work did I do? Well, it was n work, because for each row, I had to just compute where it starts and stops. And there's n rows overall. So O of n work over there. But we've already counted one O of n. And so the second O of n just doesn't have an impact on the big O notation because we can just drop constants. So let's continue to try to populate these row lists here. So let's just iterate over this columns array. So this first 0 tells us the following, that there's a non-zero entry in row 1, column 0. So if there's a non-zero entry in row 1, column 0, what I have to do is in column 0 say that there's something in row 1. So there it is, I've entered that 1. Then I know that row 1, column 3 has an entry. So column 3 has an entry in row 1. Then row 2, column 1. So column 1 has something in row 2. Then row 3, column 0. So that's this number here, row 3, column 0. So column 0 has to have a 3 in it. And then row 3, column 2. So that's this 3 right there. And now we've iterated over all of these, and we've populated all of the row lists. And so you can do a similar thing for data. I won't do it because it's essentially exactly the same. But the question is, how much work did we do over here to basically populate these row lists and iterate over everything? Well, we did O of m work because there are m entries, m non-zeros in this columns array. So that's why over here we have a plus m, because that's the work that we did here. And similar, we'd have another m that comes out of the data array, but we can drop constants, and so that other m doesn't matter. So it took us O of n plus m time to start with compress sparse row and go to CBLL. So another point to make here is that whenever I'm doing these additions, writing down this 1, this 3, this 2, these are just inserting inside of a linked list. So each of those is just order 1 time. So very fast. So the next plan, so remember our goal here was to start with A and CSR and conclude with A and compress sparse column. So right now we started with A and CSR, and now we have A in column-based linked list. So the next step that we have to do is go to compress sparse column. So let's do that. So here it is, compress sparse column. I need an index pointer. I need a row array and a data array. Okay, so let's try to do this. So index pointer always starts with 0. Okay, so over here, it looks like I accidentally dropped a number. So let's try to remember what that was. So I need column 0, row 3. So this is a 3. Okay, so index pointer, I have to add the lengths of all of these lists sequentially to get the rest of the numbers. So the next number here is going to be 2, then a 3, then a 4, and then a 5. So I added the length of this guy, the length of this guy, the length of this guy, and then the length of that guy. So how much work did I do to create all of these numbers? Well, for each one, there was just one addition, and there are n of these, so order n work here. So this is going to be O of n plus maybe some other work. So now let's construct the row array. So for the row array, we have to just copy down all of these numbers. So 1, 3, 2, 3, 1. So how much work overall here? Well, to write all of these things down took O of m. That's because there are m numbers here equal to the number of non-zero entries in the matrix. So that gave me a plus m over here. And a similar thing for the data array. It's going to take me O of m to just iterate through everything and write down the data array. So together, it takes me O of n plus m time. So as a whole, this entire process first took me O of n plus m, then another O of n plus m. So in total here, it takes me O of n plus m, applying our big O simplification rules where we drop constants. So we can go back and answer that this took us O of n plus m time. So, but let's be a little bit more careful about this and ask a few more questions. So the question I have is the following. So there's another way to do this, which is we can start with compress sparse row and reconstruct the entire matrix A, and then from the matrix go to compress sparse column. So my question is, how long does this take to construct the entire matrix A? Well, to construct the whole matrix, I actually have to write down all of the entries of the matrix. And this matrix has n rows and n columns. And so to write the whole thing down is going to take me O of n squared, which is just n times n, because I have to write down each one of these things. So O of n squared time to construct the matrix. And over here, to construct compressed sparse column, it's going to take me O of n squared time again, because I have to read what's everything is in the matrix. So there's two paths to do this. There's this path and then this path. And one of these is better than the other. In particular, this path right here, the one that gives us O of n plus m time, is a lot better. And that's because m is always, m is always less than or equal to n squared. So this path right here can only possibly be faster than this path. So this is kind of the slowest you could possibly do, and this is faster. And so that's why the answer here is O of n plus m for 7b. Okay, so that's the basic deal with uh, translating matrices. But there's another reason that I asked this question on the homework assignment, because it's going to come up in class again very soon. So suppose I have a graph G, and I'm running some algorithm that calls successors very often on G. So that means that to have successors be fast, I'm storing G in something like compressed sparse row, because we know that successors is O of 1 time in compressed sparse row. So the algorithm first does this, but then later on, it's going to want to reverse the graph. So here is the reversed graph. And call successors in this reversed graph. So to get successors to be fast in the reverse graph, what we basically have to do is take the adjacency matrix of the original graph and convert it to compressed sparse column. So this is exactly what I asked you to do in 7b. Start with a matrix in compressed sparse row and turn it into compressed sparse column. So you know that this is going to take us O of n plus m time. So before we can even start executing step 2 over here, we have to do this translation, which requires some time. So that's kind of the purpose of asking you part B of question 7, or partly one of the purposes of asking that question. Okay, so let's move on to the next problem here, which is number 8. So number 8a, all of you know the answer to that. We did that in lecture, the length of index pointer columns and data. But in 8b, I asked you what's the runtime of inserting into various sparse matrix formats. So inserting in a dictionary of keys matrix, that just takes O of 1 time, because the only thing that you have to do is add a new key value pair to the matrix. So that means that if somebody comes along and says in position ij put in value d, this is just a hash table insert, so very, very fast. So what about in RBLL? If somebody comes along and says make entry ij, it used to be a 0 and now make it into D. Well, if we go back and look at one of these linked list formats, then if somebody wants me to insert something into row I, column J, what I can just do over here is just jump to the right column and just put in the row number right here into the rows list. So putting in a new number into the rows list is very fast. Is just O of 1 time. And so inserting into RBLL is O of 1 time if you know the entry is a 0 previously. Now, if you didn't know that the entry was a 0 previously, you actually have to go and find this ijth entry. And to find the ijth entry means that you have to actually iterate over this list to see if row I appears somewhere in there. And so that's going to take you a little bit longer. So if we don't know the entry is a 0 ahead of time, then it's going to take us O of the max degree, because you actually have to find that entry. So so there's a bit of an asymmetry here. So if you knew that it was a 0, it's a little bit faster than if you didn't know that it was a 0. So that's for RBLL. So what about for compressed sparse row? So insert into a compressed sparse row. So let's go back and look at this. So let's just think about our compressed sparse row right here. So if somebody comes along and changes this 0, let's say, to let's say a 7, then what that's going to do is it's going to actually change the values of all of these entries in index pointer. So to change those entries is going to take me O of n time. The next thing that it's going to do is it's going to make me put in a number right at the beginning of this array. So I have to put in the number 0 over here because now I have a non-zero entry in column 0 in row 0, column 0. So to put in that 0, I have to copy this whole array over. And so copying that whole array is going to take me O of m time because that's how big the array is. So in total, I have to update index pointer O of n, and I have to copy the data in column array, which takes me O of m. So together, inserting in CSR takes O of n plus m time. So this is significantly slower than any of these other formats. So basically, many computer programming libraries don't even let you do this. So if you try to insert into a compressed sparse row matrix, they'll just throw up an error instead of letting you do that. And that's because a person who hasn't thought about this carefully wouldn't know that inserting into a compressed sparse row matrix actually is very, very expensive. And so if you wanted to create a matrix, you should use something like dictionary of keys because it's very fast. And then if you needed that matrix eventually in compressed sparse row, you just need to do a translation after you create the matrix from dictionary of keys into compressed sparse row. Okay, so that concludes our discussion of number 8. So let's do number 9. So in number 9, I asked you to multiply a sparse matrix times a dense vector. So the problem setup here is this. So here's our matrix A. It has n rows and n columns. And I said that in one of these rows, let's say this one, only k of these entries, so only k of these are non-zeros. So everything else is 0 except this middle part here. And we're going to multiply this by a vector v. And this vector is non-zero everywhere. And we're going to get some kind of answer out of that. And so the question is, how much time would this take if A is stored as a sparse matrix? Well, how much time does it take to just compute the very first spot of the answer here? So the very first spot of the answer comes from multiplying this first row of A times this vector. And so to do that multiplication, I don't have to multiply these 0 entries because I know their answer is going to be 0. So the only thing we have to do is multiply these k non-zeros times the corresponding k entries of the v vector. So that's O of k multiplications. And then I have to add all those numbers together, which is another k additions, but it doesn't make a difference in terms of big O notation. So order k time to compute this entry right here. But I have to do it for each of the entries of the answer. And overall, there's n entries. And so taken together, it's O of n times k time to compute the whole answer if the matrix is stored as a sparse matrix format. And this is true of all of our sparse matrix formats. But for number 9, I asked you to just give me some pseudocode for doing this with a dictionary of keys. So the key with a dictionary of keys is that, unlike in our picture here, we can't just multiply the first row, then the second row, then the third row, and so forth. Because the dictionary of keys matrix is going to return us the values in whatever order it happens to iterate over its hash table. So the only thing we can do is something like this. So for entries in the dictionary of keys hash table, and entries basically give me a ij value, which is the key, and then they give me a d, which is the value. So what I mean here is that when I get this ij and the d, what that's telling me is that in row I, column j, this value right here in this box is a d. And so what do I need to do with that value? Well, I know that I can take this d and multiply it by the jth entry of v. So this is the jth entry of v. So here it is. I'm taking d and multiplying it by the jth entry of d. And then I know that that's going to go into the ith spot of answer, because that contributes to the multiplication of the ith row times this v vector. So let's do that. So to do that, we initialize answer to be an all 0 vector of length n. And then here all we have to do is that answer I is equal to answer I plus this multiple. So answer I is kind of accumulating all of the multiplications that we're doing. So this is our idea of how to multiply a DOK matrix by a vector. So let's see how long this takes. So to initialize this vector, if I have to write down the zeros, it's going to take me O of n time, because I have to write down n zeros. Inside of this loop, one of these multiplications and addition steps just takes me O of 1 time, because there's just a single multiplication and a single addition. And then the number of times that we have to repeat this loop is going to be once for each non-zero entry in the matrix. So how many non-zeros does this matrix have? Well, we have k non-zeros in each row and n rows overall, so we have n times k non-zeros, which means that this loop right here is going to take O of n times k time. So overall, when we add these together using our big O notation, just takes O of nk time. And so multiplying a DOK matrix by a vector takes O of nk time. And you can do this with any sparse matrix format, because iterating over the locations and the values is just as easy regardless of what format the matrix in. It could be in one of the column formats, and any of the row formats, etc. So that's the answer for number 9. And let's just talk about the last one here, which is number 10. So in number 10, I asked you to give me a graph with 1 billion nodes. And kind of the main punchline here is, first of all, 1 billion's a big number. There's not that many things in the world that we have 1 billion of. But the other punchline is that you can take any set of billion objects and any relationship between those objects and create a graph out of it. So in the answers, one of the examples I have is just take photographs, and if 2 photographs share the same object, then put an edge between them. So that immediately creates a graph. And so that's kind of one of the reasons why networks and graphs are so common, is because you can use them to describe any relationship. Edges just describe relationships between objects. So the other punchline of this billion node example is that very likely in whatever kind of example you came up with, you have 1 billion nodes, but the number of edges that each node has is much, much less than 1 billion. It's probably something like 100, maybe 1,000, maybe even several thousand, but either way, it's going to be much less than 1 billion. So all of the graphs that you gave as examples are quite sparse. They have a lot less edges than they could have. And so that's another reason why sparse data structures are important, is because in pretty much every application that we look at, we have a lot fewer edges than we potentially could have. And so the last little punchline of this problem is the following, that it doesn't take a very big graph to have a billion edges. So the only thing that you need to have a billion edges is about 40,000 nodes. Because if I have 40,000 nodes, I have the potential of about 40,000 square edges, which is already over a billion. And so even on relatively modestly sized problems with about 40,000 nodes, you already have just gigantic adjacency matrices. And so unless you're really using one of these sparse formats to store the adjacency matrix, then your computations would just be very complex and difficult to execute in a computer. And you might not even have the memory to do it. So that's basically concludes the review here of homework assignment 0. And this is pretty much all that we're going to get to in class today. So thanks a lot for listening, and I'll see you all tomorrow.